In this video, we're going to take a look at using Excel with the central limit theorem.
For all of the means questions, we're going to look at the same scenario, which is using values from the CDC that said that the average total cholesterol level for an adult in the United States is 197 milligrams per deciliter with a standard deviation of 35 milligrams per deciliter, and that the population is normally distributed. And what all of that means is that if I take a look at the normal model, that I can put 197 in the middle, and then as I move to the right, I can add 35, which is the standard deviation, and then I can add 35 again and add 35 again, and I can subtract going to the left, and that should take care of about 99.7% of my values. Now, keep in mind that if I were to find a z-score for those, that would be a z-score of 0 for the middle, 1, 2, 3 to the right, and -1, -2, -3 to the left. Again, because a z-score is the measure of how many standard deviations our value is away from the mean. So, the first question actually is a question that we would have been able to answer from last week's information when we first learned about the normal model. This is talking about the population, and population and sample are different things. So this week we're learning about the central limit theorem. So we'll get to that when we get to questions B and C. But for question A, we're finding the probability that a randomly selected adult from the population will have a total cholesterol level of less than 183 milligrams per deciliter. So just as we did last week, I'm going to use the norm dist function, and x will be 183 because x represents the observed value. And then we're going to enter our mean, which is 197, our standard deviation, which is 35, and cumulative means, do you want that value all the way to the left? Yes, I do. And so my solution is 0.3445, or about 34.46%. Now, question B is the exact same question, except that instead of something from the population, we have a sample of 100 adults. So what the central limit theorem says is that if you continue to take samples of size n, or if you increase the size of n, you'll get closer and closer and closer to the real normal model, which is what we used here. But if you're using samples, you have to change the standard deviation. So for question A, we used our standard deviation of 35. For questions B and C, because we're dealing with a sample, and whenever you deal with a sample with means, we're going to find something called the standard error. Now, your book does not call it the standard error. Your book just says, take the standard deviation, that was horrible, take the standard deviation and divide it by the square root of n. And so we're going to take, 35 divided by the square root of n, and n is just the sample size, so that's 100 in this case. So I get 35 divided by 10, or 3.5. Now the good news is you won't actually have to compute this. We're just going to let Excel compute it. The reason I wanted to compute it is I wanted to show you how this model changes. If we have 197 in the middle, and instead of adding 35, I'm adding 3.5, well, all of a sudden this is now 200.5, 204, 207.5, and then going to the left, subtracting 3.5, I get 193.5, 193, and 190, and then 186.5. Now again, why does that make a difference? Because question B is almost exactly the same question as question A, except that we have a sample. And now if I look for that value for part A, 183 was somewhere in here between the mean and the first standard deviation to the left, and so it makes perfect sense that my solution was about 34.45%, 46%. For my second question, 183 is not even on here. It's to the left of any values that I see. So when I find this probability, that probability better be really, really small. So let's take a look, see if we're right. I'm going to take exactly what I did here and paste it, and the only change I'm going to make is that I'm going to take this 35 divided by the square root of 100. And you might be saying, why don't you just put 3.5 in there? Because remember, we're lazy and we want to let Excel do all of the work. So what does that value mean? Well, that value says that wherever your decimal is, this E -5 says take your decimal and go 5 places to the left. So this is basically 0.0000317. A very small number. Now, does that make sense? Yes, it does, because we drew our picture. So if you're having trouble visualizing what's going on, draw the picture every time. It's very helpful. For the last question, we're looking at, again, a sample. So I'm looking at this normal model, and I'm looking for a level of more than 190. So a couple of things to remember. First of all, 190 is right here, and if I'm looking for more than that, then I'm going to go to the right. But remember, if I use the cumulative function at 190, it's going to give me all of this area to the left. So whenever I'm doing a more than question, just like last week, I'm going to have to put 1 minus. So it's 1 minus norm dist, and it's 190, comma, mean 197, comma, standard deviation 35 divided by the square root of 100, and cumulative. And of course that makes perfect sense because almost all of my curve is highlighted or colored in pink, and so the fact that that value is really close to 1 makes perfect sense. Now, below here, I haven't talked about any of this, and I haven't talked about it because this is the way that I do, say, my certifications as I'm working through them. But it's important to understand what we did up here, because if you understand what we did up here, this is not confusing. All I'm doing is I'm putting an input for mean, which is 197, standard deviation, which is 35, sample size, which is 100, observed value for, say, B is 183. And then let me show you what I've done here. For standard error, which you don't have to call it that, you can say standard deviation divided by the square root of n, but it's standard error. So notice I've just taken my standard deviation and divided it by the square root of the sample size. And that's going to compute standard error for me. So what have I done over here? Well, I'm doing exactly what I did in question A for population, and notice those two answers match up. And I'm doing exactly what I did for question B under sample, and notice those two answers match up. And then for question C, again, remember our observed value was 190, so now I can just change that to 190 instead, and I can see that for the sample, those values match up. For the population would be like question A where it says 1 adult from the population. So again, make Excel work for you. This is very handy to just have these input boxes and then let Excel do all of the work for you. Okay, let's look at the remaining 2 questions for this particular example. And again, we're using the same mean, the same standard deviation. It's still for a sample of 100 adults, so notice I've just copied and pasted our second picture. So we're going to be using the standard error for all of these and not the standard deviation. So let's talk about how we can do this, because these are tricky, and so you have to kind of wrap your mind around what's going on. So the first question says, what's the probability that a randomly selected sample of 100 adults, so again that's just telling us, guess what, we're using standard error, from the population will have a total cholesterol that differs from the population mean by less than 10 milligrams per deciliter. So we're expecting 197 milligrams per deciliter. And so if it's saying differs by less than 10, we're saying, okay, we could go 10 in this direction, which would put us at 207. Or we could go 10 in this direction, which would put us at 187. And a difference of less than 10 would be anything between those two values. So that's a heck of a lot of area. That's a lot of area. And so what we can expect when we find our result is that it should be really, really close to 1. All right, let's move on. What else do we need to know? Well, the other thing we need to know is that these guys and the tails are equal. So what I want to do is I want to find the area of one tail. And then if I take it times 2, what's that going to do? Well, that's going to give me the left tail and the right tail. And then what do I need to do? Well, that's going to give me just the area in the tails, and I don't want the area in the tails. I want this big area in the middle. So I need to take 1 minus 2 times the area in the tails. Because if I find one tail and take it times 2, that gives me both tails. If I take it away from 1, since the whole probability equals 1, that gives me what's left over, which is what's between the 2 tails. So let's take a look at what that looks like in Excel. Equals 1 minus, because that's going to take away whatever I find for my 2 tails, and then 2 times norm dist, and again 2 because there's 2 tails that are completely equal. You could find each one separately, but that would just take more work. X is going to be 187 because again that's the value that would be 10 to the left. So that's the only actual math I had to do. The mean is 197. The standard deviation is 35 divided by the square root of 100, and always cumulative. And notice that value is really stinking close to 1, and that's what we thought it was going to be based on our picture. So we've done well. Now let's look at E, the probability that a randomly selected sample of 100 adults, let's get rid of all of our markings here so we can mark it up again. The probability that the randomly selected sample of 100 adults will have a cholesterol that differs from the population by more than 5. So now let's take a look at 5. 5 to the left would be 192, which is somewhere in here. 5 to the right would be 202, which is somewhere in here. And we want that the population will differ by more than that. So more than 5 would be further away from the mean. So really what we're saying is we want the 2 tails. So we're going to do exactly what we did in this question, except that I don't have to take it away from 1. In my first question I took it away from 1 because I wanted what was inside. Now I don't want what's inside. I want this tail, and I'm going to take it times 2 so that I can also get this tail, because that tail is the same probability. So let's take a look. Equals 2 times norm dist, and then X would be 192. And you should always, when you're doing it manually like this, use the lower one, because otherwise it's just a little bit more complicated because we're doing the area to the right. So 192, the mean is 197, the standard deviation is 35 divided by the square root of 100, and cumulative is yes, or true. And so we get 0.153, etc. So about 15%. Now, the big question is, how do I do this without having to plug all of that in every time? And there is a way. So there's actually 2 ways to do it. So with this means question, I've actually created a differs by column, and I'll show you how I used that. And then when we look at populations in just a moment, I am not going to have a differs by column. I'm just going to have everything together. So that's why there's just one tab for proportions. So again, I could put the mean of 197 and the standard deviation of 35 and the sample size of 100. And of course the sample size is just going to get that standard error for me. And then differs by. So if I say that it differs by less than 10, I'm just going to put a 10 in differs by, and then magically it's going to show me the 187 and the 207, which were the two values, and these are the z-scores for those values should you need them. And we'll talk about formulas in just a moment. But if you'll notice, the 0.9957, that value is right here, again under the sample column. So we're not really going to use the population column. But let's take a look at where all of the formulas came from. For the population, again, the left-hand value, we're just taking H8, which is the mean, and we're going to subtract this value, and we're going to add that value. And that's where the 187 and 207 came from. And then this is just the regular z-score formula. For differs by more or less for population and sample, again, I'm using the same formula I just used. Notice here I used 1 minus 2 times norm dist, and this is 1 minus 2 times norm dist. And the only difference here is for the population, I'm using standard deviation, and for the sample, I'm using standard error. Same thing for differs by more than. Again, if I put in more than 5, so I'm going to put equals 5, and then my solution was 0.1531, and again, differs by more, 0.1531. So I get the same solutions. Again, you just want to set it up the exact same way we did it by hand, but use the cells as inputs instead. Let's take a look now at some proportions questions. And there's a couple of things I want to point out about proportions questions. And that is, first, that when we dealt with the means question, mean was just given to us. But in a proportions question, our mean is actually p. And that has to be a value between 0 and 1. So in this case, it's estimated that 8.3% of Americans have diabetes. Then I'm going to write that as 0.083. And again, I'm just turning that decimal into percentage into a decimal, so we always move it 2 places to the left. So that's P. The last questions that we were given some sort of standard deviation, and in this question we will never be given a standard deviation for proportions, so we will have to compute that by taking the square root of PQ over N. And so in this case, I'm not even going to compute that because I'm too lazy and I want Excel to do it. So I'm going to show you how to let Excel do that for you. So let's take a look now at our first question. And again, the first 2 questions will be the less or more, like we started with means, and then we'll use central limit theorem with differs by questions for proportions. So, first question, what's the probability that less than 7%? So remember, this guy right here in the middle would be 0.083. And I'm not going to do all of the values again because I'm too lazy to find the standard deviation, but I know that 7% is somewhere to the left of this, and we want less than that. So this should be less than 5%, I'm sorry, less than 50%. So let's go ahead and do the math. I'm going to put equals norm dist, x is the observed value, 0.07, mean is 0.083. Remember, you always have to put those between 0 and 1. Standard deviation, this is where I have to let Excel do the hard work. So just make sure you enter it correctly. Square root, and we want the square root of all of this. So I can't close the parenthesis for square root until all of this is computed. I should point out that while P is 0.083, I didn't talk about Q. And in fact, your book doesn't even call it Q. Your book says P and then 1 minus P over N, which is the same thing because Q is 1 minus P. So again, let Excel do the work for you. So I'm going to take the square root of P, which is 0.083, times 1 minus 0.083. Notice I've created a new parenthesis and closed that parenthesis, but I haven't closed the parenthesis on the square root. And then divided by n, and n is our sample size, and it says 74 Americans. So 74, and then close the parenthesis. And now I'm going to do a comma, and now I'm looking for cumulative, and that of course is going to be 1. And that gives me a value of 0.3426-ish. Let's go ahead and talk about the bottom portion as we go this time. So typically I don't do that. But the mean, again, is 0.083. My sample size is 74. My observed value for A is 0.07. And let's talk about where the standard deviation came from. Again, I'm taking the square root of H12, which is the mean, and then 1 minus H12, which is exactly what I did up here, and then divided by H13, which is the sample size. I'm taking the square root of all of that, so that's the standard deviation. So I could have just done it as part of this as I did up here, but I didn't want to do that. I just did a separate calculation to make it easier. And then notice for less than, I'm using H14, which is my observed value, and then mean, and then standard deviation, and then 1. So I'm doing the exact same thing. So now let's take a look at B. What's the probability that more than? Well, by now we should know that more than means it's 1 minus less than. So more than 10% would be 1 minus less than 10%. So I'm going to do norm dist, and x is, oops, 0.1, because 10% as a decimal is 0.1. The mean is 0.083. The standard deviation is the square root of 0.083 times 1 minus 0.083. This is where this gets really old and where you really want to have this bottom portion figured out. Divided by 74, close the parenthesis, and then cumulative, yes. And I just had a typo because sometimes I forget parentheses. But I think I got it. So let's see how I did. Again, I've got mean, sample size, observed value in this case is 0.10. And notice for more than, I got 0.2980. And that is correct. So I'm feeling okay. And again, what did I do differently down here? Nothing. I just used the inputs instead. Now let's take a look at the differs by. Again, these are the tricky ones. So for the first one, it says the proportion of people in the sample who are diabetic differs from the population by less than 1%. So again, we're taking a look at the area between two values, because 1% to the left would be 0.073 and 1% to the right would be 0.093. So on the last examples, on the central limit there with means examples, I'll click back over there real quick. Remember, I had a special place for differs by. I wanted to show you that you don't have to have that. So the only thing I'm going to do here is for my observed, I'm just going to give the lower of the values. So in this case, I'm going to put 0.073. And so we'll make sure that that matches up to what we do by hand up here. Again, if I'm looking for the probability that the proportion differs by less than some number, remember I'm going to take 0.073 and then find this area and then I'm going to multiply it by 2, and then I have to subtract that from 1 to get the area in the middle. So I'm going to take equals 1 minus 2 times, and then norm dist. X is 0.073. Standard deviation, the mean is 0.083. Standard deviation, still the square root of 0.083 times 1 minus 0.083 divided by n, which is 74, and then close the parenthesis and cumulative. And so I get 0.2448, and that's what I have here. And again, I set this up exactly the same way that we just did it together. I just used inputs for mean, sample size, and of course the 0.073 instead of doing a separate differs by column. And then for the last one, again, differs by more than. So in this one, instead of subtracting from 1, I'm going to not subtract from 1. So more than 2% would mean that I would go 2% in this direction, which would be 0.063, and it doesn't even really matter what this one is because I'm just going to find this area and take it times 2. So again, I'm going to take equals 2 times norm dist. X is 0.063, so that's the one you have to get right. Mean is 0.083. And then standard deviation is the square root of 0.083 times 1 minus 0.083 divided by 74. And then cumulative is true. So let's see how I did. If my observed value is 0.063 and differs by more, we get 0.5329 and 0.5329. And again, I've also set up a z-score area, and you should be very good at finding the z-score by now. So it's just observed minus expected over the standard deviation. And in this case, it would be the standard deviation that we compute.